SwayamPrabha. Digital India. Educated India.
Welcome to lecture 5 of week 6 on the NPTEL course on Muffler Acoustics. So, in the last lecture we stopped at the analytical solution of a conical duct, and we did some live examples on the transmission loss of different conical mufflers. Just to remind ourselves, what we did in the last class was basically analyze configurations like these ones, the ones that are noted here. So, this was a conical chamber is more like a gradually varying area flare with a constant slope or a constant flare angle, and it could be used as a simple expansion chamber muffler like the one that is mentioned here, configuration 2, where I am pointing, or it could be used something like a diffuser kind of a thing, and obviously this particular thing has a much better transmission loss performance. But then there are configurations also where conical flares are used, the ones where I am highlighting here. So, now the thing is, we also talked about, since this course is specifically focused on only mufflers and not on horns in general, or not on physical acoustics, we would probably like to stick to only those gradually varying area configurations which are sort of commercially more used. Now, having said that, conical mufflers are used, but then such mufflers probably can also be used in a number of interesting ways. For example, let us talk about a configuration something like this. You have your extended inlet, but instead of a constant cross section area, you have a gradually varying flare, and you have things like this. So, what I would do is basically draw something like this. Okay. So, now we have already seen a very similar configuration in our last few lectures, but what is so special about this one? We will get to know that in just a minute. So, as we can clearly see that the radius is changing. So, if it is R1 at the inlet and R2 at the outlet or the other side, or vice versa, that would mean that the area changes finite or is varying gradually, it is varying linearly because it is a cone. And so, what we intend to do here is to basically analyze the transmission loss performance of such configurations. Often such configurations are used in your two wheelers or basically other places where only limited area is available in one at one place, and but gradually more space is available towards the end. Two wheelers are a good this at the beginning of this week, and they use popularly such mufflers there. The problem really here is that to analyze the wave propagation using Webster's horn equation, when you try to solve this for sections like this, unfortunately there is no analytical solution for such a system. Analytical solution does not exist. Basically, for areas in which wave propagation is in the annular region, where the annular region is comprising of a space that is bounded by a uniform duct and gradually varying conical flare. If you fix your x coordinate somewhere like here x, so what will be your area? S of x is equal to pi into dz square or dx square, I am sorry, by 4 minus pi by 4 into d naught square, where d naught is the say the diameter of the inlet pipe. So, the flow comes here, goes like this. So, again you are basically the idea is to use Q1 and Q2, where Q or QW1 QW2, where QW1 and QW2 are like the gradually varying area quarter wave resonators formed at the inlet and outlet. Now, it is difficult to find out the analytical solution for this guy for this equation, where Sx is equal to gradually varying area flare, that is the conical area minus the cross sectional area of the inlet pipe. Because once you put this guy here differentiate, so analytical solutions probably would not exist, and you might consider expanding this as a power series expansion and truncating it to a finite number of terms based on the frequency and all that sort of a thing. So, you can define certain series and you can get some an approximate analytical solution for such things, but for a general case, what we have to do is basically look for more general techniques which can be applicable to any sort of a problem. Power series definitely will help, but then again one needs to look for the convergence, and expressions becomes a little tedious as we go up for higher order terms and so on. So, basically we need to solve this equation. Of course, there is no mean flow involved here. So, and for the general case, that is your duct is like this, it need not be conical, it can be general, and then we apply it to a a popular configuration like this one, and later on something like this configuration where this is bounded by a perforated bridge to guide the flow and make it sort of acoustically transparent, the perforates, and yet your resonators will do the job. So, this is the perforated section, and your flow is there. So, but we will probably worry about this later when we talk about perforates in the next week perhaps, but for now we are not probably interested in doing this. So, I rather rub it off and focus only on this problem. So, how do we go about it? How do we exactly solve the problem? So, to do such a thing, let us consider the figure shown here. It is a schematic where we see a gradually varying area duct. These discontinuities are really notional, they do not quite exist, but what we have done is that if I just zoom this figure, we will see that this is a gradually varying area duct, and it is divided, just for our simplicity, into a large number of small parts such that each part is a uniform duct. So, what is happening at the interface between, say, this duct and this duct, what is happening? So, basically what is happening is there is a discontinuity, there is a sudden area discontinuity. So, otherwise how would we model? Of course, there are a couple of more techniques to model such gradually varying area flares of a general nature numerically, but right now this method is based on dividing the entire length into small segments such that this length is very small. So, let us look at this figure. So, this is pretty much sort of equivalent to the other figure that I had taken from some reference from some article. So, here we have a general gradually varying area duct and divided into small parts, each of length say delta x, and 1, 2, 3, 4 like this, n are the notional segments each of uniform cross section, and 1, 2 the numbers that are written not in circles, they are just the nodes or the discontinuity number. So, what happens really at the discontinuity or a sudden area jump, that we have to see. Basically, all these things are kind of a system of small concentric circular ducts or any shaped duct, but with area discontinuity at the interface, that is the key. So, this such a method in which model a gradually varying area flare with short concentric uniform pipes with jump area or jump discontinuities at the area interface is called the segmentation approach. Let me reiterate here that there is no mean flow here. So, mean flow would obviously complicate things in terms of how do you model things, basically variation of state variables at the interface, but right now we will probably just think along the lines of a stationary medium. So, what happens at the discontinuity? Let us look at this figure again. So, let us call, probably we can have a look at this as well. Let us call the point that is just here, somewhere here, or maybe just have a look at this one. So, let us focus on the node 2. So, the point or the node at or the basically the plane at which we are looking at the state variables, acoustic pressure and velocity, that is located in the duct 1, but just at the interface. Similarly, there is another node that is located in the duct 2, but it is pretty much at the interface. So, basically we are worrying about things that are happening at the interface named number 2 here, where I am pointing, and we like to relate the state variables within the duct 1 and 2. How does it vary? So, basically it is the same thing. Let us introduce a convention that pressure in the ith. So, you have your system like this, things like this. So, let us introduce, this is say I minus 1, I and I plus 1. So, at this point what happens is that P and P of I minus 1 is equal to P at I, or acoustic pressure tilde, and the mass velocity is the same, V I minus 1 is equal to V I, that is whatever mass that goes here is going here. So, this is basically we are kind of considering the discontinuities here, the notional discontinuities, just as if it were a regular discontinuity. So, the regular relations that would be valid for a sudden discontinuity like this, what we were analyzing so far, that also holds for this one. So, pressure across this interface between duct I minus 1 and I, that is the same, planar wave front propagate, and your mass velocity or the fundamental mode, that is also the same, mass velocity or volume velocity. You know, we can easily get it when we integrate the acoustic particle velocity and then in either of the chambers and integrate also over the annular region, we can clearly show that this relation also holds. So, what it would mean in terms of, if we write, let us write it down, P I minus 1 and V I minus 1 is equal to 1 1 0 0 times P I and V I. So, this is essentially an identity matrix, that is the acoustic state variables, acoustic pressure and acoustic mass velocity, that is the same. So, they across the discontinuity, across the jump, they are related by a identity matrix, there is no difference, this is a continuity. Let us say the length is delta x, delta x. Okay. So, what happens across or over the wave propagation that occurs here? How is the thing related? So, as we know, let me go to another slide perhaps. So, P I and V I at x is equal to, let us say this is 0 and this is delta x as we saw. So, at x is equal to say 0 is related to this one as C cos of k naught times delta x j. Now, this is crucial because that is how we will update the area. So, j by y I. At x is equal to delta x. Now, we get this. After this, what we know, what happens to P I and V I minus 1, say let us say at x is equal to delta x, here it will be some delta x for this duct and this is x is equal to 0 and that is for this duct, and here we have this thing. So, basically what happens is that if we were to relate the acoustic pressure and mass velocity at x is equal to delta x, or the I minus 1th segment with the things at the other discontinuity. So, what will we get? We will get P I V I times x is equal to 0 and so identity matrix times this this particular matrix. So, this is 2 cross 2, this is cos j y I sin j by yi sin cos and this thing. So, x is equal to delta x. So, this is of course, I am sorry I made a small mistake here. This is I minus 1, I think, yes. At x is equal to delta x. Delta x is for for that duct, delta x, and it is like here. So, this I would be multiplied by pre-multiplied with this thing. So, I would just rather get rid of I, and so the idea is that P I and V I at this discontinuity is related to the one here by using a simple transfer matrix which is valid for a uniform duct, which is valid for a uniform duct using this thing, and where Y I most important is Y I, where Y I is the characteristic impedance for the ith duct, that is sound speed divided by the cross sectional area of the ith duct, that is for this guy here. So, what happens for the other thing? So, Y I is, note that the diameter is increasing, diameter is a function of the distance, d is equal to d of x, that is your radius or the actual distance x. Okay. Now, the thing is that this has to be updated. So, basically what we get is pi by d naught x square by 4. So, 4 goes in the numerator, and d naught x for we can evaluate it right in the middle based on some functional rule that it satisfies. We can illustrate this example for a conical duct or for the annular cavity. Now, when we go for this thing, this guy, it is d naught x also, but the diameter has sort of increased. So, in such a case what will happen is that we can easily write now P I and V I at x is equal to delta x is related to the other thing as C j but y plus 1 times s, j by y I plus 1 s into C, and here it is. And x is equal to delta x. Basically what we get is that here it was y I is equal to C naught by this thing, here it is y I plus 1 is equal to C naught by S I plus 1. So, basically how do we go ahead with this particular thing? Now, we need to probably multiply this thing. So, let me write down the cascaded sequentially multiplied form. So, we have relation between P I plus 1 and V I plus 1 at x is equal to delta x here, and now we also have the relation. Now, we get this particular thing, and now we have this particular relation. This is actually I plus 1, I plus 1. So, I will just get rid of this guy, and x is equal to delta x. So, now it is just a job of multiplying. So, you see, let me call this as equation 2, let me call this as equation 1. So, I minus 1, that the things that happen at x is equal to delta x for I minus 1, that is I minus 1th duct or notional duct, that is related to the I plus 1th duct by this thing. So, the idea is here we saw the things that happen here. Now, we are trying to relate this with this is known and this with this is known. So, we can just simply multiply this matrix, pre-multiply this matrix with the other one, or post multiply this matrix with the other ones, because this particular thing we know that P I V I, this particular thing we know for the ith duct at x is equal to delta x, we know in terms of things that happen at I plus 1 at x is equal to delta x. So, in such a case we will get, let me write it afresh, P I minus 1 and V I minus 1 at x is equal to delta x is given by C j sin y I j y I sin cos j sin y I plus 1 j by y I plus 1 s, and this is C and S stands for cos k naught x. So, C is equal to cos k naught delta x and this is like this. So, what happens now? We have to probably stop here and introspect what is happening here. Why does this method work? This is like relating things from, well, so sorry, this is plus 1, this is plus 1 and plus 1. So, when we divide this duct into this part and this is your this thing. So, we are relating things just here with the things at this point. So, we are able to multiply these two things, and like this we can continue to cover the entire duct and account for whatever variation we are able to see. So, now let us get back to this figure where you have this kind of a discontinuity. If we were to write the pressure here, pressure and acoustic velocity here with one that is here, so it will be simply multiplying matrices with the characteristic impedance being constantly updated at each cross section. So, P V at x is equal to say 0 and it is divided into n number of segments. So, n, what are those n segments? Those n segments are here. So, it is as simple as writing P V is equal to, well, I will just say C j s y, let me call it 1 j by y 1 into s into C, then you have C j s y 2 j s y 2 C. So, this will continue with like this. So, this will continue like this at x is equal to L, where y 1 is equal to C naught by S 1, y 2 is equal to C naught by S 2, y 3 is equal to C naught by S 3 and y n is equal to C naught by S n, where now S 1, S 2, S n, these are all the cross sectional areas of the uniform duct. So, when we have such a system in here, so let me zoom it. So, S 1 is the cross section area, let me call it this area where I am pointing of the duct 1, S 2 is the cross section area measured from here till here. Like this we traverse the entire duct, and in principle S can vary arbitrarily. It can be a exponential horn, it can be a parabolic horn, it can be a conical duct, it can have some annular cavity with extended inlet and outlet, and large number of such things can be done. So, it is about gradually writing a simple for loop code. I can sort of write a pseudo code, or I can probably demonstrate that in the MATLAB just in a while. Some simple area discontinuity, I mean basically cascading of area discontinuity matrices, and then multiplying it with a duct transfer matrix for uniform duct and generating the entire system of equations, deriving the overall transfer matrix or the overall 4 pole parameters for a gradually varying area duct of any profile. That can be easily done in a simple MATLAB code, and then we will do that just in a while. And then there are other techniques also, which is known as a matricent approach, in which basically although we will not be covering that just now, maybe not in today's lecture, but just to get you a feel of that, I will show some nice photo here where you get this kind of a thing. So, here what happens essentially here, this is yet the same duct, but divided in again notional segments such that there is no jump discontinuity. So, what happens essentially we will probably worry about the maths later on in the probably in the week 8 or probably towards the end of week 7, when we have just introduced a CCTR, a conical concentric tube resonator, in which such techniques often are handy. So, as a stepping stone to the main CCTR problem, we will be considering again the gradually varying area duct problem without any perforates, using the matricent approach, where the ducts are modeled as notional segments, but with small segments of exponential profile. So, this is approximately a short exponential profile, such that the discontinuity is not there, and for an exponential profile we know the transfer matrix. So, then it is just about matter of gradually multiplying the transfer matrices and getting the solution. So, we could do that and analyze a CCTR using a matricent approach also. What we will do now, we will have a look at a simple conical duct example, exactly what we saw in the last lecture, and possibly for the annular cavity as well. And there is yet another system that is used, that is a short end chamber cavity, in which the wave propagation is along the transverse direction. So, I will probably talk about that after finishing that case. Look at then this figure. Well, this is something like a also known as a multi-pass perforated duct silencer. Is basically you have a outer shell. You can also have a look at perhaps this figure. So, what it does is basically it shows you there are two configurations. The overall shell is elliptical in shape, and you have two perforated ducts, also in general known as multi-pass perforated silencers. So, such silencers are used invariably in a lot of modern day commercial vehicles, and the good thing about such silencers is that it is able to pack in a lot of transmission loss, lot of attenuation, good attenuation performance, even when you have limited space, because the waves have to go through multiple perforated pipes and there are number of end cavities, quarter wave resonators. But then it allows the flow, the way it does is basically it forces the flow to basically undergo a number of turns. So, if you have a look at this figure, this configuration, it basically takes at least one reversal. So, it is called a flow reversal configuration also. Here it is able to, is basically forced to take 3 reversals, 1 and then 2, and actually 2 reversals, but then there are 3 perforated pipes. Because most of the thing is used in the middle chamber, at the end generally less space is available, although there is no hard and fast rule that the end chambers have to be small, but generally they are the end chambers, where I am pointing here, this one and this guy here is generally short in length. So, such cavities are called end chamber, short end chamber cavities. They are of elliptical shape because of the overall shape, because of space constraints, or they could also be circular in shape. So, in such a configuration, especially when such a thing is an elliptical in shape, highly eccentric ellipse. So, for such a thing, if you have one port here and one port here, and you have a configuration like this, something like this, flow comes in here and it leave here. So, the entire idea is that the wave propagation is along the transverse dimension, but again it is not a uniform section if you do it like this. It is uniform only along the axis L, but along this direction, along the major axis, you can consider this duct as a duct of gradually varying area duct. So, for such a thing, we again have to resort to numerical approaches like segmentation approach or a matricent approach. So, based on the time permitting, we will probably take up this case now, probably in the later parts of the course, when I talk about some design criteria, we can do that as well. Now, before we end this lecture, let us do a quick demonstration of a gradually varying area duct, a conical duct analyzed using the segmentation approach. So, let us analyze this a conical duct. Before we go to MATLAB, let us also look at the general relation. Let us say we measure the distance x here, and at this point we are having a radius r. So, what happens, what is the radius at a distance say x here. So, let us say this is r of x. So, r of x minus r or r naught by x is tan theta, is not it? This angle is theta. So, this is like this, r x is equal to r naught plus x into tan theta. So, we get this kind of a relation. Now, we will keep this handy, and let us now, it is time now to finally enter into MATLAB thing. This is the transmission loss. So, like I have been mentioning, MATLAB scripts are usually best written as function files, also known as subroutines in Fortran, but we will work with MATLAB, and this is the transmission loss plot, more like an overarching routine which calls yet another routine transmission loss, where the transmission loss for a given frequency is computed, and which is your this part, and this calls the most important routine, the heart of the segmentation approach. The file is named as segmentation approach. So, this is what it is, and segmentation approach is basically this is the file. Now, it takes in few parameters, namely the frequency f naught or FREQ, at which the transmission loss is to be computed, radius r, which is the radius at the right at the inlet r naught, and L, that is at the section 1 where the flare just begins, and L is the overall length or the conical section. Theta is the flare angle. Usually if it is more than 4 degree or 5 degrees, flow separation would happen. So, it is generally not more than 4 or 5 degrees. We will take probably the case of 4 degrees for numerical purpose. N is the number of parts or number of small segments into which the conical duct is notionally divided. So, it can be 100, 200, we can do some convergence analysis on the transmission loss. Choice is nothing but basically whether you want to do it using a segmentation approach or a matricent approach. We will not be worrying about matricent approach right now. So, we will just use the choice one, which is for the segmentation approach. CH1 is nothing but it's more like a which kind of a configuration we would like to analyze. We would probably like to analyze a conical expansion chamber of configuration where ports are on the opposite end faces. Reversal type of configuration is something where the ports are located on the same end face. So, we will not discuss that in this lecture. We will worry about only the expansion chamber in ports are located on the opposite faces. So, this routine in turn called the shape profile. So, what does the shape profile do? Shape profile basically, these are all commented parts on the top. It again takes in the few parameters, the r which is the radius at the inlet, theta is the flare angle, delta z is a small part over which the duct is assumed to be uniform. So, delta z is already defined here, I guess. Delta z is L by n divided into n parts, as I noted before, and I is the section for which we need to compute the radius, that is the ith part, and n is the number of your such parts. So, what happens now when at the first section x is equal to 0. So, the radius becomes at equal to r naught or r itself, but if I is between, if it is not equal to 1 and not equal to the last part, then we take the middle part of that as an approximate thing, that is x1 is equal to I minus 1 into delta z and I into delta z. The average of that, for safety we are taking that as the approximate x value over which the increment in the radius has to be computed, and when I is equal to n, x is equal to I into delta z. So, the radius at any section r, capital R as a function of x is r small r plus x into tan into theta. So, theta you have to be careful, it is given in terms of the degrees, but we have to convert into radians before we use this. So, that is what we have done here, and this gets you the shape profile radius, and then it gives you it basically computes a transfer matrix for a cylindrical tube here, that is basically this part, cos j sin y, j sin by y, cos k naught L, all these things it computes in the form of P pressure and the mass velocity. If it is a matricent approach, it follows a different sort of a slightly different form of a transfer matrix. So, anyways, we will worry about work only with this part. So, this function gets cylindrical function gets invoked, it finally throws up the T parameter, transfer matrix parameter for the small notional segment. Now, here is the heart or the holy grail of segmentation approach. So, once we get T, now A is initialized with I matrix is nothing but a unity matrix 1 0 0 1. So, initially let us say when I is equal to 1, that is we are traversing just the first segment. So, identity matrix times the T matrix for the first segment. So, A becomes T after the end of this operation, and these things are cleared, and the loop goes back here, the radius is updated, and the transfer matrix which with appropriate characteristic impedance is obtained, and that is multiplied by A. A was T I, where I is 1. So, T1 into T2. So, A becomes T1 into T2, and then again the loop enters here, R is computed for the third section, then transfer matrix is obtained and A is equal to A1 into A2 into A3 and so on. So, like this, once we do that, we get the transfer matrix, or we get the transfer matrix of the overall duct. So then once the program exits the loop, for the expansion chamber, overall transfer matrix is nothing but the cascaded matrix A itself. Now, once we do that, we can pass this to the function, the calling function, which calls segmentation approach, named as transmission loss. It basically computes your transmission loss as usual, what we have been doing in the last classes, as some summation of the transfer matrix parameters appropriately scaled by the characteristic impedance. Now, here R inlet and R outlet are the radius of the duct and the outlet duct, inlet and outlet duct, which can be same or different from the radius of the inlet and outlet section of the conical duct. So, this is the plotting thing which we have been discussing. So, R inlet and R out, what I mentioned, R we have basically these two, and the theta parameter in a hand, R inlet and R outlet we can also fix. So, let us do some parametric studies. We will there is something which I have already done. Expansion chamber I have mentioned, K is the color of the graph, and 100 parts I have mentioned that, and this is the segmentation approach what I have asked the function to do. Frequency is from 5 hertz to 2000 hertz in step of, or maybe 10 hertz we can do in steps of 10 hertz just for demonstration purpose, and 75 is, let us say, the inlet R naught value, basically 75 mm. So, 75 by 1000, 300 mm we could have written it like this, and let us make it more practical. 25 mm is the radius of the uniform pipe at the inlet, and 25 mm is also the radius of the outlet pipe at the larger section, and 4 is the flare angle, which is of course we are supplying that in degrees. So, let us evaluate the transmission loss for this thing. It will take a few minutes based on the processor speed. So, we get again the same dome and trough configuration, but the troughs are lifted up, they are not the same, and as the flare value increases, angle or the radius at the outlet section, these values would actually go up. So, we can demonstrate that, but what we will probably do is that we will hold on to this figure, we will hold on to this figure by command hold on, and plot it with a different color, but larger number of segments, 200, double of the last one. So, the conical duct is divided into exactly the double number of segments. So, the graphs are nearly identical. I can just sort of remove or get rid of this part, and they are identical. I mean, like this, if we do for 400, 800, we will see the results have converged, and it will match exactly the analytical thing, although we are not sort of comparing it right now. So, this is one part, and another thing what I wanted to quickly mention here is that if we go with 75 mm here and 75, look, the thing is that let me just compute it for you. The angle is tan D 4 degrees into the length is 0.3, okay, and this is the inlet radius is 75. So, what will be the radius of the outlet? So, it is basically your answer into 1000, that is your 95 mm, 95.7. So, why am I telling you this? Now, let us say you look at the other configuration what we discussed. Inlet section, the radius of the inlet pipe is the same as the inlet section. So, we have the radius 75, and this radius is 90 it was probably 95.87. We will plug in this value and have a look at the things here. You will get a decaying curve, not your dome and trough thing. It will be evident in a minute. Yeah. So, we see the same decaying thing. So, this approach is actually indeed working fine, and like this we can in principle evaluate the complicated sections like I mentioned at the beginning of this lecture, which is this section annular duct. We just have to take care of this expression and update the area change accordingly, and get the overall transfer matrix for from this part to this part, compute the impedance here, similarly for this part compute the impedance here, and then regular cascading of transfer matrices we will multiply this. In principle it is possible to analyze any duct using the segmentation approach, and it is a very good numerical technique, robust one. We will stop the lecture here, and what we will do in the next week is going to be very important, week 7. where we will introduce the effects of mean flow more formally, although we have done it to a certain extent in the lecture week 2, the last few lectures of week 2, where we talked about the convective Helmholtz equation involving the convective effects of mean flow. But basically what we are going to do is that we are going to talk about aeroacoustic state variables, which basically involves the effect of mean flow, where Mach number m naught is much less than 1, typically 0.1, 0.15, that is a max that happens in automobile or automobile exhaust systems. We will talk about the aeroacoustic state variables, we introduce that, and then we will kind of have a look at different perforated duct configurations and different expressions for perforate impedance. Basically across the perforate there is a jump, there is a pressure jump. So, we are going to model that using the appropriate functions, and then once we do that, using a planar wave analysis, we will start analyzing simple CTRs, concentric tube resonators, and duct with a concentrated perforated tube and so on, and then we will keep analyzing different cross flow configurations, straight through configuration, and all those kind of things. Some of that would probably involve MATLAB coding, and then gradually build upon the stuff that we have learned in week 6 on gradually varying area ducts. So, week 7 and I guess to a certain extent of week 8 is going to be very interesting in terms of, because we will talk about directly about the perforates, a very practically important, a very important element. So, till that time stay tuned and keep looking at the lectures and noting down your doubts and all that sort of a thing. We will probably meet in the next week, week 7, we will introduce perforates. Thanks.